Okay, let's get rolling. So, like I said, I'll start this off with the same disclaimer I gave last time. Right? Not by any choice of mine, it's just the nature of the material. It's going to continue to be pretty derivation heavy. I have made up a couple of examples to throw in here to try to illustrate the math that we're going to be going through, but it should all culminate on Friday when we come up with the famous Navier-Stokes equation. So bear with me here. Today we're going to be wrapping up what we didn't get to last time, which is understanding the way that fluid stresses act on a fluid particle. Okay, and through this we're going to differentiate what we call body forces and surface forces. These were introduced in Chapter 2, Hydrostatics. Since I didn't do the lectures for that chapter, I don't know whether those were covered by Professors Mentia or Eichinger, so we'll gloss over those topics today. And then by the end of today, we should have the general equations of motion for a fluid. Okay. So quick little recap. Last time was a bit of just a progression through a bunch of vector math and vector calc, but we derived last time the continuity equation from the principle of mass conservation. Okay. And we gave this in three forms. The first was that ddt of the density plus the gradient operator dotted with the product of density and velocity equal to 0. The second was the material derivative of density plus the divergence of the velocity is equal to 0. And these two versions of the equations are exactly equivalent. Okay, it's just a matter of how you group the two terms, or how you group the terms together. Okay. And we had one simplification that said if we have incompressible flow, this signifies that the density of a given particle cannot change. Okay. In other words, that the material derivative of the density has to be 0. Okay. And in that case, we can cancel out this first term, and we end up with grad dot v is equal to 0. So that's you know, in a few inches of page space is a summary of everything we did last time. Okay, so today we're moving on from conservation of mass into conservation of linear momentum. Again, something we covered for big integral control volumes before, but we need to shrink down our domain from being a sizable region of space to a single point in space. And this is going to open up the door to the equations of motion for a fluid, like a generalized fluid as a continuum. So, big picture here. This is going to motivate today's progression. Conservation of linear momentum. Okay, we know this more familiarly from dynamics and physics as what? Newton's second law, right? Or F equals ma, or force equals the rate of change of linear momentum. So Newton's second law, which says that the sum of the forces, sum of the forces is a vector on a system is equal to the rate of change of the momentum of that system. Okay. so I'm skipping a bunch of steps right here, but there are two ways we could apply this to a tiny little cube of fluid. So if we said we have a cube that's delta x by delta y by delta z, we could go through the process of actually applying the Reynolds transport theorem to this tiny, vanishingly small cube and take the limit as delta x, delta y, delta z all approach 0. Or we could say, let's take a systems approach and let's treat everything in this cube as a system and apply Newton's second law as a system. Either way you do it, and I believe they're both in the book, what you're going to get is that applying this to this, the sum of forces on this little volume, and I've included a delta F here to imply that small volume, you're only going to be able to apply small forces to it. It's equal to ddt, the small mass of that particle fluid, m, okay. So basically we're saying this small little cube of fluid is going to have some small mass associated with it, some volume, or some velocity of the fluid in that cube. If we were to take the time rate of change of this in a Lagrangian sense, okay, because the mass doesn't change, right? The mass of a system has to remain constant. Then it simplifies to this expression right here. So we have mass times the rate of change of velocity. Rate of change of velocity is acceleration. So we end up with our regular old F equals ma. Okay, familiar expression. This should not be a surprise. But I have skipped some intermediate steps in the derivation of two endpoints there. Okay, so the idea here is we're working with then the sum of all the forces on a particle of fluid is equal to the mass of that particle of fluid times its acceleration. We need to start to figure out how we write the two sides of this equation. Okay, if this is the equation of motion for a fluid, in chapter 4 we figured out how to write the acceleration. Right, this expression right here, the material derivative, we've done that. If given a velocity field, we can write the acceleration field given the information there. In other words, we know that a is equal to time rate of change of v plus v dot gradient v, right? Material derivative. This is a definition that we have been through. So we've got the right-hand side of this equation pretty much all wrapped up. The question is, how do we figure out what the forces acting on this particle of fluid are? And so that's the point of today. So take this. Okay, so we have two types of forces that act on a particle of fluid. There's first what we call body forces. Okay. Now these are generally distributed throughout the fluid volume, and because of that, the resultant of all the body forces acts through the center of mass. So examples of what we would call body forces include things like fluid weight, right? Gravity pulls not just on in a particular location in a fluid, but pulls on the fluid as a whole, okay? Gravitational acceleration is throughout the fluid, and so where would we put the resultant force due to gravitational acceleration? Right at the center of mass, or the center of gravity, okay? So we'll call this gravitational weight. Things like magnetism, okay? If you have a ferrous fluid, you know, one of these fluids that actually is magnetic properties, and you apply a magnetic field to it, it's going to apply a force throughout the volume of that fluid with a resultant force that acts through the center of mass of that fluid. And there are a few other examples. For example, the virtual force due to centripetal acceleration, okay, or the centripetal force is another example of a body force. But as a general rule, the only one we are really going to worry about in this course is gravitational weight, okay? So, only one we So as a little schematic here, if we consider our fluid, we might have, we might say, right, the weight of that fluid acts at the center of gravity. If there were some magnetic field, maybe it'd be pulling in this direction. Okay, but in both cases, we put it at the center of mass. The other type of force, those we call surface forces. Okay. And these result from, say, the pushing, pulling, or friction of surrounding particles, whether they're fluids or solids, what have you. Okay. And the reason we call them surface forces is because they act on the faces of our fluid element. So for example, we might have a frictional force on this face, frictional force on this face. There might be something pushing or pulling on this face over here. But notice they are all being applied to the external faces of our fluid cube. Examples of this, there are really only two. Okay. Pressure and shear stress. So body forces are generally really easy to, they're really easy to understand. Okay, it's you know, fluid weight, or the gravitational acceleration times mass is something that we're all pretty familiar with. These surface forces are a little bit harder to calculate, okay, or a little bit harder to represent. So we're going to focus on those. Surface forces. We'll say that surface forces are described using a stress tensor. Okay. So I'm going to have to, oh, 1 second, I need to find my picture that I drew. So we're going to consider a cube of fluid. Okay. In other words, this is some So cubical element of fluid. The gray, of course, signifies the fluid itself. And the back corner here is located at the origin. We would say that we've got 6 faces on this cube, each of which is going to have an area. We'll describe those areas, this one, as delta A x, okay, because its normal vector points along the x-axis. In other words, the normal vector is the I unit vector in vector space. This face we would call delta AY. Similarly, its normal vector would be written as J. And then this top face would be delta AZ. And its normal unit vector is K. All right. The faces that are not that are hidden from us, those on the opposite sides are going to have the same areas, delta AX, AY, AZ, and the normal vectors are obviously just going to be pointing in the opposite direction, so negative IJK. Oops. So each of the 6 faces, right, can have 3 forces acting on it. We'll go ahead and write those as delta Fx, okay, in the I direction, delta Fy acting in the J direction, and delta Fz acting in the K direction. Okay, I'm color coding these so that they make it more straightforward as we draw them onto this. If you guys can tolerate me being a little decisive here, I'm going to make all of this text black so that the forces, when I draw them in color, remain a little bit more obvious. So the forces in the x direction, right? We could draw here, draw them here, draw them here. In the y direction, here, here, here. Z direction, here, here, here. So we've got our delta Fx, our delta Fy, and our delta Fz. Okay. To avoid clutter, I won't draw them onto the back faces, but assume that they apply over there as well. How do we define a stress? Okay, what 2 quantities? Like it's the quotient of what? Force over area, right? So, using that information, the stress tensor is going to be defined as tau ij is equal to force J over area I. So we could write, for example, that tau xx is equal to delta Fx over delta Ax. Okay. This is what we call a normal stress, okay, because we've got delta Fx for area x. It is acting in the same direction as the normal vector, meaning pushing or pulling on that face. For normal stresses, we have another symbol we use, which is sigma xx. Call this a normal stress, which is related to pressure. tau xy is going to be delta fy over delta ax. Okay, so that would be this guy right here acting over that face. And tau xz is delta fz over delta ax. So these two are what we call our shear stresses. So a few extra, a few kind of notes or important things to remember when we're talking about stress tensors. The sine of tau ij is going to be equal to the sine of fj times the sine of the normal unit, or the normal unit vector I. In other words, what we've drawn here, what this is saying is that if the force is acting in the positive coordinate direction and the unit vector of the face it's acting on is also in the positive direction, then the stress will be positive. If they're both acting in the negative direction, it'll be negative. But if one's positive and one's negative, you're going to end up with a negative stress on that face. Sigma xx is equal to sigma yy is equal to sigma zz, which is the negative of the pressure at a point, and tau ij is equal to tau ji. In other words, our stress tensor is symmetric. Okay. Any questions about these definitions? Why is it symmetric? So it has to do with, there's a identity that we're not going to get into, but as you take the volume of this and take the limit as this cube shrinks down to a point in space, it ends up being that when you set up the equation of motion for rotation, like if you take, here, simple version, take a box like this and we've got, basically, let's say we've got tau ij, we've got tau ji. These two are going to be creating opposite moments about the center of the box. And as you take the limit, as the box size approaches 0, that moment has to approach 0 with it. And it just ends up being that the volume approaches 0 fast enough that those two have to converge towards each other. Another way of thinking about it is that, no, actually that explanation is not going to make much sense. But it has to do with the rotational equilibrium of a point in space. Okay, so I'm going to borrow my picture again here. A little bit of practice naming the fluid stress tensor elements. So we'll call this A. Call this one B. Call this one C, and we'll call this one D. Okay, so turn to whoever's sitting next to you and try to come up with a consensus for how we would write like tau xy, negative tau xy, come up with a sign and the subscripting for the stress tensor elements that we would assign to each of these. For example, for A here, right, we would say the unit vector is pointing in the z direction, right? So this is delta AZ for this face up here, okay? What direction is the force facing? In the x direction, but is it positive or negative, okay? The unit vector is in the positive z direction, the force is in the negative x direction. So we would write that A, okay, is negative tau zx. So, I said, try to whoever's next to you, work on B, C, and D, and I'll kind of cold call on groups of 2 to try to help me fill out the rest of these. So take the next 2 minutes.
Well,
All right. Who's got a guess for B? I guess I'll say I'll be cold calling in groups if I don't get volunteers. So save each other. Anyone got a guess for B? We got tau yz. All right. Reasoning. It's on the y-facing face. It's acting in the z direction. It's acting in the positive z direction, and the face is pointing in the positive y direction. So it's positive, positive, tau, y, z. Okay. What about for c? If I didn't explain this before, but I drew this with a dashed line open circle to show that it's on the far face here. I was hoping that would be clear, but yeah.
Negative tau xy.
Negative tau xy. Okay, let's that one. So, what direction is the force acting in? The x direction. Okay. Which means that if we look up here, I had to switch subscripts on my own on the notes a couple of times, but that comes as the second subscript. Okay, so and the face comes as the first, so it would actually be tau yx. Technically, you're also right because they're symmetric, but okay. Now, which direction is the force acting in? Positive x, negative x? Negative. Okay. What direction is the normal vector on that face pointing in? Negative. So negative times a negative is going to give you a positive value, actually. Okay. So, okay, that was the tricky one. Oops. And D. Yeah. Tau xx. Okay, so the force is pointing along the x-axis, right? And it's an x-facing face. So your subscripts are right, but it's at negative tau xx. Good. Negative tau xx, because the normal vector on this face points along the positive x. The force is acting along the negative x. Oops. All right. So cool. So we've talked about, we've gone through this idea of the stress tensor and how we describe like the way stresses are written out. Yeah.
Sorry, can you say again for part D why exactly it's negative? Because we were looking at that and I was saying force is acting in the negative x direction and it's going opposite of our normal vector.
Exactly. That's why. So if you take the sign of the force, the sign is negative, right?
Yeah.
Then if we drew the normal vector, okay, on here, it's pointing in the positive direction. So the sign negative, sign positive, right? This is also a good illustration of why when we do the normal forces, okay, we can also write this one as negative sigma xx, right? Before I said sigma xx is equal to sigma yy is equal to sigma zz is equal to pressure, right? If you have a positive pressure, that tends to create compression, right? It would be pushing in. But a positive pressure is equal to a negative normal force, okay? And so this kind of confirms that sign convention. All right. So the real reason that we want to talk about the stress tensor is because we want to understand how to use this. Oh yeah.
Why talk about tau if there's no radial component on the end?
Sorry, what's that?
Why talk about the stress in the context of tau if there's no radial component? And why not just talk about it in terms of sigma?
There's no radial component.
Like it's causing rotation.
So, okay, I see. So in other words, if there's no fluid rotation, where is the shear stress coming from? Sort of is that the question?
Or why not just talk about it in terms of sigma as opposed to not?
Well, because sigma is the special name we give to the one where the stress is acting in a direction that is normal to the face. Okay, but the shear stresses, the ones that act tangentially to the face. We're gonna actually on Friday's lecture. The idea is we've established this idea that that Newtonian fluids, right? That tau is equal to viscosity times the gradient of the velocity, right? And in the last week we talked about this thing called the rate of strain, right? This gamma dot that can be written using velocity gradients. what we're going to do next lecture is plug those two ideas together and show how these shear stresses, tau xy, yx, yz, zy, how these can all be calculated using the velocity gradients. And that's going to close the loop on this set of equations of motion. But the idea here is, however you're creating these stresses, right, it's literally just that friction force of one fluid against another. We're not talking about how the fluid is moving yet. But the idea that there's no rotation really just comes down to, like I said, it's a mathematical proof.
Yeah.
But it's not saying that the fluid is actually, quote unquote, irrotational. It's simply saying that that where you have two forces working in that sort of meet at a corner, or two stresses that point towards the same corner, those two balance each other out just through the math. Okay, we can, if you want to, come do derivations during office hours. I'm happy to oblige. But, all right. Okay. The forces that result from these. Okay, this is really what we're driving at here, right? We want to populate that F term in the F equals ma equation. So we're going to do this in a very abbreviated fashion. Paste another copy of this. There we go. Forces resulting from fluid stresses is the next part. So I want us to focus on the x direction only for a second. In other words, I want to write all of these elements of the stress tensor that involve a force acting in the x direction. Those are over here, okay? The positive, or this would be written as tau xx, right? Or sigma xx. We'll go ahead and write sigma. Sigma xx. On the opposing face here, we would have sigma xx plus. And here's our first order Taylor series expansion that we all love to hate. Xx times delta x. Okay, we're saying that this guy is delta x in this direction, delta z tall, and delta y in this direction. Similarly, on let me draw this in a different color. On the bottom face here, okay, we would have tau zx, and over here we would have, oh sorry, I pointed that in the wrong direction. That should be going that way, and this one should be going this way. This one would be tau zx plus partial z of tau zx times delta z. And then finally on the y faces, we could write, this is always where things get really crowded, I apologize, but, we would write, this one is tau yx plus delta y, tau yx delta y, and then over here we would have tau yx. Okay, so we basically said we've got sigma xx, sigma zx, tau zx and tau yx acting on the faces that all have coordinates of 0. And then if we took a first order Taylor series expansion to extrapolate those out to the faces that are delta x, delta y, or delta z away from the origin, that's how we would write it, using a Taylor series expansion. If we wanted to write out the surface forces acting in the x direction here, we would have xx, right, plus x, tau xx dx times the surface area over which it's acting minus tau xx delta y delta z, okay, plus, and then you would do the same for the tau yx, tau zx components. Okay, we've been through this process before, but what we're going to end up with then is partial x of tau xx plus partial y tau yx plus partial z of tau zx times delta x, delta y, delta z, where we can also write this as sigma xx. So we could write it either way. What if we wanted to include the body force? Okay. Before, right, the body force would simply be located at the center of mass and pointing in whichever direction gravity is acting. Okay. Gravity isn't always acting in z. If, for example, our coordinate system were tilted, our gravitational acceleration might have a component in x, y, and z. So rather than this is a mess. We'll go ahead and call this FB, okay, or delta FB. We say that delta FB is equal to, right, the mass, delta x, delta y, delta z. So density times volume times the gravitational acceleration. And so we could write delta FB in the x direction, because we're looking at the x direction only, rho delta x, delta y, delta z, times the x component of our gravitational acceleration. I'm zipping through this pretty quickly. I apologize, but I need to get to, I've got a way that wraps this up fairly nicely, if I can get PowerPoint to play along. Okay. So, conservation of linear momentum, right? Basically, mass times acceleration is equal to the sum of all the forces. Those forces come in two flavors: surface forces and body forces. So in a kind of a word equation, this is what we're working with. Our surface forces, which we just derived, we've got x, y, and z components. We derived this x1, right? So partial x of the normal stress, partial y of the y component shear stress, and partial z of the z component of the shear stress in the x direction, times delta x, delta y, delta z. Same thing applies for the y and the z components of those forces. Okay? Body forces. In the x direction, the one we just derived, density times volume times gravitational acceleration along that coordinate direction, equal to the mass, right? Density times volume times the acceleration of that component. We've shown previously that the acceleration of a particle, okay, this fluid particle we're talking about, can be written as the material derivative of the velocity. And then applying the material derivative equation that we've gotten before, we end up with this expression right here. The one change we're going to make to all of this is we would say, look, we've got this obnoxious delta x, delta y, delta z in all of these terms. So we would cancel every single one of, keep the row. We would cancel out the sort of the volume from every one of these terms. Okay. And what we would end up with on our general equations of motion is right here. Okay. So we've got our body force per unit volume over here, our surface force per unit volume, and over here we've got our mass times acceleration, again divided by our little the elemental volume. Okay, and I say divided by the volume because we crossed out that delta x, delta y, delta z in the previous slide. These are given in the book as equations 650. And these are what we call the general equations of motion, or the momentum equations for a point in fluid. But this is the reason I like to spend time on this, is because I want to make it clear that like these are already some nasty looking equations, and on Friday we're going to make them a lot nastier by using models for how the shear stresses come from fluid kinematics based on Newtonian fluids. But at their heart, they're really actually quite simple. It's literally just F equals ma. Okay. The Navier-Stokes equations that come from this, also F equals ma. And we'll try to hammer that in so you understand what each term comes from. This is one of the big takeaways from fluid mechanics, is understanding that everything we're doing is conservation of mass, or F equals ma. That's really, that's all of it. Okay. I've got only about 4 minutes, but that should be enough to at least walk through the steps for an example problem that I made up that'll help with the homework. You'll note that tonight's homework is only one problem. It basically comes to plugging in known values into those equations of motion and trying to find the unknown. But if we assume that we've got steady flow in 2 dimensions, u is given as 3xy, v is given as negative 3 halves y squared plus x squared. We know that in this case we'll say that g is given as negative 9.81 meters per second squared in the j direction. So we'll say y is the vertical. And we'll say that sigma xx is equal to sigma yy equal to, negative pressure equal to negative rho g y. Okay? So hydrostatic pressure gradient. So this is our given information. We might be asked to find du dt and dv dt. In other words, the Eulerian rates of change of the x and the y velocities. Okay. How quickly are things changing in time? Wait, I said steady. This is not steady. This is going to be an unsteady flow. My mistake. Unsteady flow in 2 dimensions. Okay, so since I don't have time to actually do the calculations, we can at least talk about how you would do this. Let me split my screen here for a second. Okay, so essentially, it's going to come down to we've got, we're not worrying about the z direction. Okay, z becomes unimportant because we're dealing with 2D flow, and so any variations in z also become unimportant. So anything that has a derivative in z disappears. Okay, we have expressions for u, v, and sigma xx, sigma yy, okay, as functions of x, y, which means that we can actually calculate. Oh, I'm missing one thing here. Yep. We're also given that tau yx is equal to 2x and tau xy is equal to 2x. Okay, sorry, forgot those ones. In other words, we're given information about every term in here. Sigma xx, tau, sigma yy, tau, g. Okay. We're given u and v as functions of x and y, so we can calculate these terms explicitly, which means that all of those terms are going to be known. It just is a matter of taking derivatives and plugging them in and solving for our unknowns, which are du dt, dv dt. Okay? That process is what's going to get you through the homework problem for tonight. And that wraps things up. I'll see you guys on Friday.